Hello physics students, this is Mr. Dillick and welcome to physics videos 18 and 19. Today we're going to be talking about the concept of net force and equilibrium, and we're also going to be talking a little bit about the history behind Newton's laws of motion and Newton's first law of motion. Okay, so let's dig in. At the end of our last video, we talked about the idea that you might draw a free body diagram to analyze the forces acting on an object. For what purpose? Well, the main reason we draw free body diagrams is so that we can determine the net force. And the reason we want to know the net force is because we want to know if the forces are balanced or unbalanced. Why? Because whether or not the force is balanced or unbalanced tells us which of Newton's laws of motion we should apply to that situation. So what is the net force? Well, that's actually kind of a slippery question. When asked for the net force, there could be three things that I'm asking you for. One, I might be asking you to add up all the forces, but only in one particular direction. And that's what's often called the directional net force. Now, the directional net force basically comes in three varieties. There's the net force in the x direction, the net force in the y direction, the net force in the z direction. That is, are the forces, when I add up all the forces that are either going either left or right, and I ignore all the other forces that might be going up and down or forward or back or somewhere in between, is one of those forces winning, and by how much? If there is a force that's winning, it's a net force. If the two forces are equal, if they're balanced, then there is no net force, and that's a situation we call equilibrium, and I'll talk about more of that later. Okay, so directional net force is something we're often asked for, and the only way you could know which of these three versions of net force I wanted when I was asking you in a certain question about them is to pay close attention to the context of the question. So if it's interested in only the forces in one direction, that's the directional net force. Then there's the total net force. Now, the total net force is the sum of all the forces accounting for all directions. So that means we are not interested in just the forces left and right, or just the ones up and down, or just the ones forward and back, but we're interested in all directions. And this is usually a two-dimensional force. That is, it usually has to be given not only with a magnitude, but also a direction in terms of an angle. And then the third type of net force is actually not a sum at all, and we're not adding up forces, but instead we're doing a multiplication. We're finding the product of mass and acceleration, and that's calculated by Newton's second law of motion, which we'll talk about in our next video. So just table that for now. Okay, so what are some examples of calculating the directional net force? Well, let's take this one for example. Okay, imagine we had a situation where we had an object, and that object is on a surface, and it's experiencing four forces. The force of gravity is always a force that acts on an object, so it's acting down. The normal force, because it's on a surface, it's touching that surface, and the surface touches back. And then two applied forces. Anytime we only have one applied force, we usually call that FA. But if we have more than one applied force, we generally call them forces 1 and 2 and 3, and so on and so forth. So here's force 1. Here's force 2. Force 1 is a little bit bigger than force 2, and that's why it's called force 1. We generally number them by magnitude. So the largest force gets the force 1, and the second largest force gets force 2. So force 1 is a little bit bigger. So what if I asked you for the net force in a particular direction? What if I asked you for the net force in just the x direction? Basically what I'm saying is, forget this force because that's vertical, and forget this force, it's vertical. If I add just the two forces that are horizontal, force 1 and force 2, together, what number do I get? Well, if these are balanced forces, that's going to add up to 0. If this force is, say, 5, and this force is also 5, then technically this one is positive 5 because the positive direction is to the right, and this one is negative 5 because the negative direction is to the left. And so we might say plus 5 plus minus 5 equals 0. So balanced forces are going to add up to 0. On the other hand, if this, the way I drew it, is not balanced, that is, force 1's a little bit bigger than force 2. Let's say force 1 is 7, and positive 7 because it's to the right, and force 2 is negative 5, 5 to the left. Then when we add those two together, we're going to get a net force of plus 2, which means that the force to the right is 2 newtons bigger to the force to to the left. It's basically a tug of war. And force 1 is winning by how much? 2 newtons. In which direction? To the right. And then, as you're going to learn, Newton's second law says that that is going to be equal to mass times acceleration, which we'll come back to later. But if the forces are unbalanced, we're going to say that the 2 newtons of net force is going to be equal to the mass of this object times its acceleration. Okay. Well, like I said, we'll come back to that later. All right, what about total net force? When we're dealing with total net force, as I mentioned, we tend to deal with forces that are two-dimensional. Let me give you an example. All right, so there's a lot here. Don't get intimidated. Pretty much what we're looking at here is an object that is falling but has an applied force pushed to the right. So imagine that something was falling but there was a strong wind blowing it to the right. So it's actually going to likely move kind of in that direction because it's being pushed down and to the right. So it's moving in that direction. So this is the direction the net force would be acting. Another way of saying the total net force, or net force in general, is to say it's the sum of all the forces. So in this case, the sum of all the forces is what we call the net force. It's the sum of all the forces in the x direction, this way, and all the forces in the y direction, this way. So in this case, because there's only one force acting in the x direction, the net force is the applied force. Let's just pretend that was 3. And in this case, because there's only one force acting in the y direction, the net force in the y direction, these are directional net forces, is gravity. And let's just pretend that that was 4. Well, based on that, we have a 3, 4, 5 right triangle. So the net force would be 5. It's the sum of these vectors. And so I would just use Pythagorean theorem to find that. And because it's two-dimensional, I would also need to find the angle, which is the inverse tangent of 4 over 3 in this case, which is about 53 degrees. So to state the net force, total net force correctly, I would say it's 5 newtons, 53 degrees below the positive x-axis. So total net forces are always going to be stated kind of in that way. All right. So again, the whole point here was to determine whether or not we're in equilibrium, whether or not we have balanced forces. And there's actually 2 types of equilibrium, static equilibrium and kinetic equilibrium. If it's static equilibrium, static means not moving. Kinetic means moving. So objects that are not moving but have balanced forces are in static equilibrium. So a book sitting on a table or anything that's, not moving is in static equilibrium. That is, the net force in all the directions is 0. Now you could have static equilibrium in one direction and have kinetic equilibrium in a different direction. So the directional equilibria can be different. But the total net force is going to be the sum of all the forces in all the directions. So if we say it's totally in static equilibrium, it has balanced forces in every direction. All the forces are the same in every direction. Or balanced, I should say, in every direction. You could have a 3 Newton force to the right and a 3 Newton force to the left, and then a 5 Newton force up and a 5 Newton force down, and those are not the same forces in every direction, but they are balanced in every direction. Kinetic equilibrium is a little tricky here. When we have kinetic equilibrium, what we're saying is that the object has balanced forces, but it's already moving. So think about this. If you put your cruise control on your car, you're going to move at a constant velocity because the engine's forces pushing you forward and friction and air resistance and things pushing back are balanced. You're moving, but the forces are balanced. You're in kinetic equilibrium. So remember we said forces go with accelerations. Well, if there's no net force, then there's no net acceleration, and that's what we mean by objects in kinetic equilibrium are not accelerating. They always move at a constant velocity. So constant velocity means kinetic equilibrium. Kinetic equilibrium means constant velocity. So again, static equilibrium means the forces are balanced, and kinetic equilibrium means the forces are unbalanced. And here's a pretty important picture. Okay, so don't get scared off by all of this. Basically what I'm showing you is a free body diagram for something in static equilibrium and kinetic equilibrium. They basically are the same, except this one has an arrow, squiggly line, saying it is moving, and this one has one that says it's not. The forces on both objects are balanced. Why? Because here's what we call an equilibrium statement, a statement that is a math equation that says, look, the net force in the x direction, the directional net force, is the sum of all the forces that act left and right. So in this case, force 1 and force 2. And if it's in equilibrium, those add up to 0. Same thing here. What about the forces up and down? The directional net force, net force in the y direction, is the sum of all the forces acting either up or down, gravity and the normal force, and they add up to 0 if they're in equilibrium, and the same thing here. Well, if the forces left and right add up to 0 and the forces up and down add up to 0, then all the forces, the total net force is 0. Same thing here. But here's the big difference. Because the net force is 0, this object isn't accelerating, but because it's static equilibrium, it's also not moving. Whereas in kinetic equilibrium, the acceleration is 0 because it's moving at a constant velocity, but that velocity is not 0. Okay, so that is basically the idea of net force and equilibrium. Okay, so on to video 19 here. We're going to talk basically about a little bit of history. I mentioned earlier in the video that we're in a branch of physics that's called dynamics. We're explaining why things move instead of how things move. Well, how long have people been interested in why things move? As turns out, it's been a long time. Aristotle wrote the first laws of motion ever. He was a philosopher, so they weren't scientific laws, but basically he said that things move based on whether or not they're made of a certain substance. And I talked about this in class a little bit, but earth, wind, fire, and water are what he thought things were made of. And so he said boulders tend to roll down mountains because they're made of earth and they want to get closer to the earth. And fish tend to flop when you take them out of the water to get back into the water because they're made of water, so they move to get near water. He was wrong, but it was a pretty good explanation that lasted for a couple thousand years. The first people to really say, maybe you're not right, were ancient astronomers. And as early as the ancient Romans, people were saying, well, things seem to move differently in space than they do on Earth. And maybe the laws of motion Aristotle wrote weren't universal. They didn't apply everywhere in the universe. There were different laws in different places. Ptolemy, in particular, was a famous astronomer who based a model of the universe around the Earth being at the center of the universe. And that stood for another 1,400 years before Copernicus based one with the sun at the center of the universe. Both of those are wrong. We know that our solar system is not at the center of the universe, but at least they were trying to explain why things move in a certain way. Galileo is really the father of physics. He's the one who wrote the first truly scientific laws of motion that replaced Aristotle's laws, but it didn't happen until about 1500 or 1600 AD, so not until about 400 or 500 years ago. And then Newton took those laws that Galileo wrote and added math to them. So let's take a look at what Galileo said. Galileo basically said, he coined the term acceleration and the term inertia. And he basically said if an object isn't moving, it has static inertia. And if an object is moving, it has kinetic inertia. Static means not moving, kinetic means moving. We talked about that already. Now, he didn't give us any math here, but basically he defined inertia as a tendency to not accelerate. And he defined acceleration as speeding up or slowing down or changing direction. So pretty much Galileo said things that aren't moving probably aren't going to move, and things that are moving probably are going to keep moving the way they do. But he didn't include math. Galileo's first law of motion is also called the law of inertia. Now, this is an Italian word, a pretty weird thing for a British guy to be using. He was basically giving credit to Galileo here, who coined the Italian word inertia. And basically, if you take a look at Newton's laws of motion, you can see that it's made of two parts. The first one is the static, and the second is the kinetic. He basically took Galileo's ideas and fleshed them out. And he added the idea of equilibrium and net force to Galileo's ideas. So we see that in his first part, he says an object that is at rest has a tendency to stay at rest, and that part's the same as Galileo. But then he adds this part, unless the forces get unbalanced. And then same thing, an object that's moving in a straight line is not going to change direction and not speed up or slow down. Those things describe acceleration, just like Galileo said, unless the forces get unbalanced. So the key thing here is that Newton's first law says exactly what Galileo's laws of motion say. Things that aren't moving because the forces are balanced on them. And they won't move unless you unbalance the forces, unless the equilibrium, the static equilibrium, gets broken. Same thing with kinetic equilibrium. Unless the kinetic equilibrium gets broken and those forces become unbalanced, an object that's moving will keep moving the same way. So this is the most important thing. Static inertia goes with static equilibrium. Kinetic inertia goes with the idea of kinetic equilibrium. And we've gone over this already, but the thing that Newton added was that this is dependent on mass and mass alone if it's static inertia, but it's dependent on mass and velocity if it's kinetic inertia. And he called that momentum, which is idea for another day.